Jorge Campos is the Director of R&D at Pavement Recycling Systems, where he is committed on the research of new ways to improve the performance of asphalt recycled materials and the development of automated systems that are used daily in their company's projects. Most recently, Jorge led the development of a new prototype process, thin lift in-place technology for the company, which was awarded a patent. That's impressive, Jorge. Jorge has a degree in industrial engineering from the Technical Institute in Mexico, so help me show our appreciation for Jorge.
Good morning, everyone. I'm so pleased to have this opportunity to present this work. Since my first attendance at the ERAT meeting 3 years ago, I was amazed of the amount of work from each of you to improve our processes. I believe that the time that I spend in this meeting is always valuable time for me, and I really do appreciate all your work. Let me say something. As an automation engineer, very often I receive calls, stressful calls from the field. They call me saying that the trains are down, right? And I need to go right away to those sites and make sure that they work. Well, nothing compares to the day that I received the email from ERA saying that they appreciate my, they appreciate to be a volunteer to speak over here. So that to me is stressful. And I didn't know nothing about that volunteer thing. So I went into my boss' office saying, I was thinking maybe by mistake they sent me the email going to my boss, right? So I went to my boss' office and I say, okay, Don, I think they sent this email, but it's meant for you. I don't think it's meant for me. And he said, oh, by the way, I volunteered you for this meeting. I said, okay, great. So what am I going to speak to? So I was thinking maybe for the new award technology, the new machine, but no. He said, can you speak about the supplemental compaction the same day? And I say, yeah, sure, why not, right? Okay, so supplemental compaction the same day. As right now, we are very limited because we need to go on every job, and every recycled job, we need to go back after 2 days and we need to re-roll that job. So that means we need to have available resources for that job, for that purpose. So can we do supplemental compaction the same day? We don't know yet. So I start looking into compaction. What is the compaction? Looking more information on compaction, and I came across with this statement, and if I can figure out how to use this, I believe it's this. Okay. So I came across with this statement that says the compaction is the single most important factor that affects the pavement performance in terms of durability, fatigue life, resistance to deformation, strength, and moisture damage. As we all know, uniformity of compaction is one of the most critical steps in the cold recycle process. We need to get the density that it will ensure the maximum performance of the material, but what's more, inadequate compaction can lead to premature failure on the pavement service life. So what we want is, and what we think is the better compaction, we're going to get better performance of the material, right? But we don't mean to go to the levels of hot mixes. We don't want to compare the cold recycle with the HMA. And I think Dr. Jones said very clear that these are two completely different materials, and we need to understand that. So what we need is the optimum compaction for our material. So, what are our goals? We need to improve the cold recycle pavement performance. We need to take advantage of the new technologies and new chemistry and emulsion manufacturing. We hear 2 or 3 beautiful presentations and, from the vendors, 2 vendors and 2 suppliers. You can get with those vendors for the emulsion and start asking for highly modified emulsions that they can perform and help you on the supplemental compaction the same day. So if we can do supplemental compaction the same day, we can minimize the delays for final surface, but also we can maximize our labor resources. Sounds really good, right? But what we did, so we determined the effects of supplemental compaction at different times and temperatures on the performance of the cold recycled materials. And we compare the same day compaction, supplemental compaction versus the traditional 48 hours compaction. So where to start? I was lost, it's a long run. So when we start with the gradations, with the materials. So we spend a lot of time in the field. We took samples of the aggregate straight from our machines before they reaches the pot mill. We remove the samples from the belt and we send it to the lab. We run sieve analysis on those gradations and we come up with something that is fairly common in our process, from our machines. And we call it RDD1 gradation. So we're going to start with that gradations. I know that there are infinity numbers of gradations, but we need to start with something, and we're going to start with something that is coming from our machines. Okay, so this is the chart. It's showing where the gradations, the RDD1, that we call RDD1, is falling into. So we are comparing our gradations versus the area medium gradations, lower and upper limits. So it's pretty much medium gradations. So this material, after we come up with this gradation, we obtain wrap from one source, and we send it again to the lab. We screen over 1 inch, and then the rejected material, the oversized material, we crush using a custom-made crusher that we design and manufacture, so we can get similar conditions to our machines. It performs quite similar to our crushers in the field. So with that, after we crush the material, we recombine the material, and we screen that material. We separate the material, we fraction the material into 11 different sizes. So those are the sizes on the bottom of the chart. We separate in all those different sizes. It's really time consuming, but we found that this is the only way that we can have some kind of consistency in our results. So we want that. We don't want to have very inconsistent results on our research. So from there, once we screen the material, we separate the material in 11 different sizes. We recombine that material following the RDD gradations, and we use that material into our research. So we have the material now. What we need. Now we need to find the optimum asphalt content and water for mixing. So we went ahead and we test for the optimum asphalt content in the water for mixing, and we follow the protocols in the area mix design guidelines. So after we after we did that, we found that the optimums for us, for our gradation, is at 3% emulsion and 2.5% water. I want to emphasize here that this engineered polymer modified is a highly modified engineer. We work really close with our supplier to get that custom-made emulsion for us. So we want to have some control, some degree of control on the braking. Then after we decide the optimums for asphalt content and water mixing, we decide to run 4 different points of cement. We use Portland cement at 0, 0.3, 0.6, and 1% without modifying the percent of emulsion. So we have the aggregate, we have our water, the emulsion, the additive. So how we gonna mix it now, right? So again, we try to mimic as much as possible the conditions in the field. So we went back into the field, we spent some time there, and we found the data shows that normally, most of the times in our jobs, the initial compaction is in between 40 to 60 minutes. We never touched that mud before that time. So we want to evaluate that in the lab. So in the lab, we perform testing. We do compaction testing at 10, 20, 30, 40, 50, all the way to 90 minutes, just to see the breaking, when the emulsion is going to start breaking in our material. Again, lab conditions, 77 degrees. So after we finished that research, we found that most of the time, at 40 minutes, the water that is coming or is pushing out from the sample is pretty much clean water, clear water. So that is telling you or telling me that the setting or breaking of the emulsion is taking place at that time, so you can start the compaction. You can leave the asphalt in the mix and just push the water out. So we decide to start doing the initial compaction at 40 minutes. For the supplemental compaction that we're going to use for our research, we want to keep the samples inside the mold. So we don't want to disturb the samples. So the samples that we're going to use for supplemental compaction are going to be kept in the mold. 2 different supplemental compactions we're going to compare, 2 hours and 48 hours. So we want to compare in between the traditional 48 hours and same-day compaction. 2 different temperatures we're gonna try. We're gonna use 77 degrees and also 90 degrees. Why? Because in Southern California, we never experienced in our busy season, which is from March all the way to November, we never experienced lower temperatures than that. But we are open to widen the brackets. All compaction, we use a super paid gyratory compactor for our research, and we use 30 gyrations and 600 kilopascals. What testing is going to be done? We're going to use air voids and Marshall stability in all the samples. Additional testing is going to be the Hamburgs, the ITSs, and the SEBs on select mixtures. Here is our data, the results. So the first graph is showing the samples without supplemental compaction. So we mix the material, we compact at 77 degrees after 40 minutes, all the samples are compacted after 40 minutes. And as you start applying supplemental compaction, you can see the increase on performance of the material, increase on stability. Then you apply 2 hours supplemental compaction at the same temperature, and you're gonna see an increase, or we experience an increase on stability. And it's looking really good, but what happened when you apply temperature? So we are expecting to see an increase, and it happened. So this is the 90 degrees supplemental compaction after 48 hours. But we want to compare that to the 2 hours. So we see an increase on performance, on the stability. This is for the dry subset, and these are the results for the wet subset. Again, this is the Marshall stability on our mixes without any cement, just using the emulsion. And you can see almost this, the same trend on the wet samples, and a decrease on the air voids as you start using supplemental compaction, either at 77 or 90 degrees after 2 hours. So we went from 15% air voids to 12% air voids. The orange line is the air voids trend. We start adding cement to our mixes, and pretty much we are seeing the same trend on both the dry and the wet samples. But we noticed something on our air voids trend. It went up when you use supplemental compaction after 2 hours. That is unexpected result on our end, so most likely we're gonna go back and redo it. But the performance of the material is still showing a really good performance when you use supplemental compaction after 2 hours. Then this is the samples, the results when you start increasing the cement without changing water or emulsion into our mixes. So the behavior of the material starts changing, and pretty much you can see the results are showing that for the same temperature, either at 2 or 48 hours, you're gonna get the same results, or we got the same results, almost the same results. Even if you change the temperature at 2 or 48 hours, the results are pretty similar. Same thing for the wet subset, but the air voids trend went back to normal. We see less air voids when you apply supplemental temperature after only 2 hours. So the behavior of the material starts changing as you increase the cement. What happens when you add a little bit more cement? So sure enough, now we have almost no change on performance if you perform supplemental compaction at 2 or 48 hours. Even if you increase the temperature, you're gonna see almost the same trend at 48 or 2 hours. The only thing that is still good, is showing the same trend, is the air voids. Applying supplemental compaction at 90 degrees Fahrenheit, you're gonna get a really good air voids percent. So we saw that. We start analyzing those results, and we decided to go ahead and test for cracking resistance in Hamburg for deformation. So we decided to run those two and compare the results with our Marshall results. So for ITS results, using 0.3 cement, we got these results. And that is, again, for the samples with no supplemental compaction at all. You can see that it's a really good performance of the material. But as you start adding supplemental compaction at 77 degrees, in this case, you don't see much of the change. But when you start applying supplemental compaction after 2 hours, you're going to see a change on performance. And I'm going to make a comment at the end of this graph, because you start seeing better PSI results on this testing. When you apply 48 hours at 90 degrees supplemental compaction, again, you're going to see an increase on performance. And finally, our 2 hours at 90 degrees supplemental compaction shows an increase on performance, even better. Same thing for the wet subset. Now, a little bit change though. The 48 hours at 90 degrees is showing a slightly better performance than the one at 2 hours at 90 degrees. But I want to make a comment on these graphs. If you see only the numbers, it shows an increase on performance, but you need, I think we need to start paying attention also to the flow, the shape on the lines. I think that's an indicator, or maybe a brittle behavior of the material. So we need to be cautious with that. So at this time, only the samples at 0.3% cement are done for ITSs or Hamburg. We run out of time. I'm pretty sorry. We tried to get as much as possible data, but we ran out of time. So here's a Hamburg test at 0.3% cement. The lines on the top are the samples that, the mixes that we use supplemental compaction after 2 hours. The black line is the supplemental compaction at 77 degrees after 2 hours, and the orange line is the supplemental compaction after 2 hours using 90 degrees. So you can see the deformation is very minimal. It's about 3 and 2.5%. The conditions of the testing, all the samples were submerged in water at 40 degrees C throughout the test, and we applied a force of 158 pounds. And the duration of the test is 20,000 passes. So after 20,000 passes, you are seeing this when you apply supplemental compaction. So we check for the cracking resistance, we check for the deformation, we check for the Marshall stability. We want to check for something more, and that's the SCB test. We are not very familiar with this test yet. We don't know what this test is going to mean for the cold recycled materials, but the picture that you are seeing right now is one sample that we apply supplemental compaction after 2 hours at 90 degrees. So even when the fracture energy is about 212 to 13 actually, but the flexibility index is 4.2. So it's normally the HMA requirements are 400 joules per square meter for the fracture energy. So we are below that, but we are a little bit, we are better than the minimum flexibility index required. So, but again, we don't know what that means for cold recycled materials. We just want to collect as much data as we can on all these mixes to see if we can have any translation, any correlation in the future for field performance. When I say performance in this research, I mean just for the lab conditions. I'm not saying that these are performance that we can correlate with field conditions, not yet. We just got these results, and now we are committed to go and do a test strip and we're gonna apply supplemental compaction to those samples. And we want to get data for the long and short performance of that material. So maybe we can see any correlation with the lab conditions, and maybe we can bring it to the next presentations to the era. So the conclusions are that supplemental compaction improves the cold recycle performance when using emulsified recycling agents. Supplemental compaction the same day, they obtain similar, if not better, results when compared to supplemental compaction, the traditional supplemental compaction at 48 hours. All testing is conducted in the lab, but the results warrant field verification. With most of the testing or most of the research, we agree that we need more testing to be done, and maybe start doing some field verifications so we can correlate these conditions. This is something that pavement recycling system is conducted using its own money, and I'm very proud of the company, because every time the company sees an opportunity or to improve the performance, it's always willing to see, to test, to research, and make sure that it's a true condition or it's something that we don't need to follow. So, but on this one, we think that it warrants the field verification. So that concludes my presentation. Hopefully, I didn't bore you.
Any questions for Jorge?
Yes, sir.
Jorge, it's not a question, but more of a comment. The slide that you showed with the ITS test results and looking at the flow, I think it's really important to consider both those components in there. But just a comment, some of the work we fiddled around with in the lab, looking at the same type of test, we got the same change in curve shape as we added cement to it. So I think it almost looks like when your curve, like you're reducing maybe more brittle behavior, because your curve is not only getting taller, it's getting
narrow, yeah.
Narrower.
Yes.
Just an interesting observation, that's all.
Yeah, I was waiting questions from you.
Howard
Yes.
Anderson, Utah DOT. When we do our cold replacement cycle, we use hydrated lime. And I was wondering how that would compare. In this case, you're using cement, which would start to hydrate within that first period. It's not too surprising that after 48 hours, you might be breaking up some of that hydration and losing strength. How would that compare if the CIR was done with hydrated lime?
We don't have we haven't done any research using that additives, so I don't have no answers. Maybe we can add into the next phase of that research. Sorry, we just start, and we are rushing to finish. Yes, sir.
What temperature do you run here on Marshall stability then?
It's the SCB from Instrotech.
What was the question? Marshall stability temperature.
Marshall stability temperature?
Yeah, the temperature you're going to test at.
Oh, no, for the temperature, we kept the samples in the mold, right? And we put it in our draft oven through the period of time, let's say 2 hours or 48 hours. We put it in that condition, or in a temperature control chamber. So after the time is done, we remove from the chamber, temperature chamber, and we put it again for recompacting the material. Yes, sir. Well, that is the most common guideline that many of the standards, they recommend to do 30 gyrations. So we stick with those 30 gyrations, but maybe in the future we're gonna increase or decrease according, and that is what is important. We need to correlate these results with field results so we can start getting some sense of what those numbers means in the field. We don't know if 30 gyrations is going to be similar to the compaction effort that we are using in the field. We don't know if we need to go back or forth. So we're going to use these numbers to correlate the compaction efforts. But we are following guidelines on that.
Also on your effort, you tested as just like asphalt, how mix under the water?
No. You mean putting a layer of asphalt and then till?
Sample that you showed, effort test?
Yeah.
I think he's asking if you do it exactly like an asphalt sample. You run the same.
Yeah. Yeah, we compact 2.5 inches sample and we run the sample in those conditions.
Okay, quick question. Excellent work. How many gyratory molds do you have?
How many what, I'm sorry?
Gyratory molds are just, that has to be
Oh, we invest on those, and we have 12 gyratory molds at 4 inches and about 7 gyratory molds of 6 inches. So we can keep the samples in the mold for that period of time.
Yeah, that's a lot.
Yeah, we had to invest on that.
Anything else?
Well,
Thanks, Jorge.
thank you so much.
Thank you very much. That's some great information, Jorge. Really appreciate it. And Don, thanks for voluntolding him. Appreciate that. We're running a bit ahead of schedule right now, so we're going to come back in here at 10:10. Give us a little extra time to fight that light traffic out there. So 10:10, we'll be back here. Thank you, guys.